Hello, so I am Marwa Tarshuri. I am a PhD student at ATEM and IUTRN. So I will be presenting today my work called the AI-based light parallel video encoder. So I will start by introducing end-to-end learn video coding. Then I will present my first contribution called learn patch coding using overlapping. After that, I will explain the adjustment of MCSIM implementation made to fit with our use case. Next, I will present PanVC framework, and I will wrap up with a conclusion. So I will start with end-to-end learn image codecs, which are image codecs based entirely on deep learning. They use the autoencoder architecture. They have an encoder that transforms the input image into a latent representation. Y. It is quantified, and then a probability model will estimate the probability distribution of those latents so that we can generate a bitstream. After that, on the decoder side, it will reconstruct the input image from the bitstream. So here we have one of the baselines in the state-of-the-art of learned image codecs. It's introduced by Bali in 2018. So in here we have the probability model based also on an autoencoder architecture. It's this part. So we called it the hyper autoencoder. So here the hyper encoder takes the latent representation, it turns it into another representation called Z that will be part of the base stream. And the hyper decoder, estimates the parameters of the probability distribution, which makes the generation of bitstream Y possible. And then the decoder will reconstruct the input image as before. So for end-to-end learn video codecs, in the state-of-the-art, we find two type of approaches. The first one, it follows the same traditional video coding pipeline, so replacing the steps with neural networks. But there are also other works that focus on deep learning techniques such as 3D convolutions, transformers, etc. So even though end-to-end learn codecs manage to achieve results that are competitive or even outperform some of the traditional codecs, they still face some limitations that made their practical use challenging. In fact, neural codecs, they are large deep learning models that are demanding in terms of computing power and hardware. So when we use those large models to code big resolution, high resolution frames, we are faced to a memory saturation problem. And as a solution to this problem, we proposed our method called learn patch coding using overlapping. So one simple way to solve the previous problem is to divide the input image into smaller patches, then use the neural codec to code those patches, and then gather the decoded patches to form the decoded frame. However, if we do that, in this case, we will have border artifacts. So our proposed solution is to use patch-based encoding while removing those artifacts. So what we do is first we divide the input frame into overlapping patches horizontally and vertically. Then we use a neural codec model to code those patches using parallelization. In our case, we trained an intra-coding model inspired from Cheng 2020 architecture. We based it on we trained it on small crubs. And we use the loss function. The loss function that we use is the rate distortion function, as distortion can be either MSE or MCSIM. After that, we gather all the decoded patches. We use a linear function to combine the reconstructed overlapping idea to remove the border artifacts. So here I present the results in terms of coding time. The coding time is computed using two different GPUs with different memory capacities, 11 gigabytes and 24 gigabytes. So as we can see, an HD frame here can only be coded using our method. We cannot code the whole frame at once since we will have an out-of-memory error. So in this case, our method is necessary to do the frame compression. However, with the smaller frames, we noticed that our method increased slightly the coding time, and this is due to the additional overlapping pixels. So here, what about phase distortion results? So this method leads to code the additional overlapping pixels in order to remove the border artifacts. And with that, we can expect a loss in rate distortion results. However, in this method too, we have neural codecs that code smaller patches, which is similar to the training condition, and a neural model always works best in the training condition. So in this case, we expect gain in rate distortion results. So let's see what happens. So here we computed the BD rate in terms of PSNR and MCSIM, and patch coding without overlapping shows that we have a loss in BD rates, which is due to the border artifact that deteriorate the frame quality. But this loss is eliminated when we use our method with overlapping. We tried to increase the number of overlapping pixels. However, it cannot be increased indefinitely, so the BD rate reached the peak at n equal to 16, and then it started to deteriorate due to the additional overlapping pixels. So here on the left, we have the visual results. Without overlapping, we have some border artifacts. With two overlapping pixels, the border artifacts are less visible, but still there. And with the 4 to 8 overlapping pixels, they are gone completely. Here we have the same result with the MCSIM models. So now I will talk about the adjustment of MCSIM implementation that we made. So as we all know, MCSIM is an objective quality metric designed to measure the similarity between two image or videos. So to compute this metric, it consists on computing the SSIM metric on multiple scales using a sliding Gaussian window. So in the classic implementation of PyTorch, at least, the sliding window works this way, which means that the borders are not considered in the computation of this metric. So when we train our coding models to optimize this metric, it tends to have a low quality at the border, which is all right if we code the whole frame. However, when we use the patch coding method, it leads to a more visible artifacts, like here. So what we propose is that we add a replication padding to the input, and then so that the border artifact, the border of the input can be considered in the computation of the metric, like we show it here. So as a result, we can see that with the adjusted MCSIM, the border artifacts are less visible, which makes removing them with our previous method easier. Also, the BD rate, here we computed the BD rate of the patch coding without the overlapping, so it's normal that we have losses due to the border artifacts, but with the adjusted MCSIM, the loss is less imported than with the classic one. Here we presented the rate distortion results of the learn patch coding method with the adjusted MCSIM. So here I want to show that with the adjusted MCSIM, only 2 overlapping pixels are necessary to remove the border artifacts, but previously we needed 8. Next, I will present PanVC as an end-to-end learned video coding framework adapted to practical application. So this framework is open source is available here. And in this framework, we integrated the previous method, the learn patch coding method, as a solution to memory saturation problem. We also explore parallelization to reduce the coding time as much as possible. And we train two independent components as an encoder and decoder, which is rare in this state of the art. Usually we have one model that do the encoding and the decoding. An actual bitstream is generated, and we compute some quality metrics to help analyze the functioning of the framework. So here we have our encoder and decoder. The encoder takes as an input a YUV video. We do some pre-processing. Then we divide it into overlapping patches. The normal encoder codes those patches. Then the hyper-encoder is applied to generate the bitstream Z. Then the hyper-decoder is applied to generate the bitstream Y. And on the decoder side, we have both bitstreams are decoded, and the neural decoder decodes all the patches. We gather them using the linear function to remove the border artifacts, and after some processing, we have our decoded video in YUV format as well. So as I mentioned before, we have two parts in the bitstream. They have approximately the same architecture. So there is a header where we find the information necessary for decoding, and then for each patch, the binary of each patch is preceded by its size, and we do that patch by patch and then frame by frame. So we do that for bitstream Z and bitstream Y as well. So to wrap up, PanVC is an end-to-end learn video coding framework adapted into practical applications. So we included in this framework a solution to manage efficiently the memory. We also explore parallelization to optimize to reduce the coding time. It's also, this framework is also designed to be compatible with the other coding models. Neural coding models. So currently we only have one intra-coding models, but in the future we aim to add more, and we also hope that it will be a tool to compare those neural codecs in a practical conditions. That will be all. Thank you for your attention.
Thank you, Marwa. One really quick, short question. Otherwise, I got to keep the schedule moving. Okay, really quick.
Hi, very interesting work. Thanks for sharing. My question is, as far as I saw, everything is done basically on a single image level. Have you looked into adding any temporal component learning?
So as I said, for now we included one intra-coding model. So even if we code a video, we do it in an intra mode, frame by frame. But as the future work, we aim to add more video models that will take into consideration the temporal part. Thank you.
Okay, thank you, Marwa, again.
Thank you.